Okay, well, let me just get into new stuff because there wasn't any homework assigned for today, and or was there? Was there? No. And then we'll just go over the test when you get it back. It's easier to do that when you have it in front of you. So let's go into the next topic, which is centroids. A centroid is the geometric center of an object. And you can do this in 2D or 3D. You know, most of the problems that we're going to do are 2D, but this idea works in 3D also. And we'll use the centroid for two things. You know, two engineering applications. We'll use centroids for. The first one is finding the center of mass. So for objects made out of a single material, that means a homogeneous material, a homogeneous body. The center of mass is the centroid. The people who've come in the last few minutes, don't forget before you leave to put your binders up there if you have them. Okay, and center of mass is important because when we treat weight as a single point force, we treat it as a point force acting at the center of mass. So far, the bodies we've used, it's been easy to just sort of imagine what the center, like the center of a rectangle is easy to imagine. It's just in the middle in one dimension, in the middle in the other direction. Same with a circle, it's easy to imagine. But for other shapes, it's not intuitively obvious, and so we need this to figure out where the weight goes. And then the second use is for distributed loads. Distributed loads are loads that don't happen at a point, but are spread out over some distance or some area. You know, over a length or an area. And, you know, it's probably worth pointing out that there really is no, in real life, there's no such thing as a point load. You know, it's a good approximation for a lot of things we deal with, but any force is applied over some little bit of area. The sharpest knife in the world, if you push it down on something that's spread out over some area with the surface. And so really, it's the idea of a point force that's an idealization. Yes? Yeah, so, well, weight is an example of a distributed load. And yeah, wind resistance is acting. Anything that's, so if you treat something as a particle, you can treat wind resistance as a point force because the thing is a particle and we're treating it like it only acts in one place. But yeah, if you want to know what the effect is of, like on the surface or whatever of something, then yeah, you have to treat it as a distributed load. Things stacked on top of other things, their weights are applied as a distributed load. It comes up in a million ways. But when you treat things as distributed loads, you need to find the centroid of the distributed load to do calculations. The centroid is defined according to this integral formula. So I'm going to give you this integral definition of the centroid, but really in practice we're just going to always use formulas that come from this integral definition. I think it might be the case that there's not a single problem you have to do in this class where you have to do the integral. That might be wrong. You might have to do one or something. But this is what it means to find the centroid of an object. In 2D, so if you're only working in 2 dimensions, the centroid, and I'll denote the centroid with that over bar, so x bar, y bar, is equal to 1 over the total area of the object times the integral over the area of the object of position xy dA. Okay, so what that means is if you break up the object into infinitesimal areas dA, x and y, and actually let me write it like this. So for each infinitesimal area dA, x bar, y bar is the location of the centroid of that area. If you're really doing it just infinitesimal, like point by point, then those are just the locations of those points. Integrate that over the whole body. You can think of it, the centroid is basically like a weighted average, weighted by the area. Because if you remember the formula for average, it looks a lot like that. And in 3D, it's the same idea, but instead of area, you do it for volume. So we have x bar, y bar, z bar is equal to 1 over the total volume times the integral over the whole volume of x bar, y bar, z bar, dv. We're going to use 2D a lot more often than 3D. So I'm going to do an example using this integral definition for a right triangle. Okay, so this angle's 90 degrees. The centroid is up here somewhere. And I want to calculate I'll call that x bar and that y bar, those two distances. Okay. And I'll call this distance B, that's the base, and this H. Okay, so we're going to use the integral definition to calculate the location of that centroid in terms of the base length and the height. Well, with any integral definition, the thinking part of it, the part that determines whether you can do it or not, is deciding what your pattern is for breaking up the shape into these infinitesimal pieces. Okay? For circular things, a lot of times you'll break them up into little infinitesimally angled wedges or something. You know, for rectangular things, a lot of times you're going to break it up into strips, like like when you first heard about Riemann sums. How are we going to break this one up? No, really, I have no idea. I was hoping you would help me. Okay, forget it. Okay, so let's put the origin there, and I'm going to break this area up into strips like this, we're going to think of this as a Riemann sum of these strips. Okay, so that's our area dA. The centroid of this infinitesimal dA is there. Use that center of mass formula. The x location so this is our x bar. This is our y bar. Just for that little dA. Remember, this formula looks like this. Is equal to 1 over the area times the integral over the whole body of x bar, y bar, dA. So what I'm doing now is figuring out how to represent these things in the integrand. The area dA is the area of this strip. The thickness of that strip is dx. And the height is y. We know that the total area is base times height over 2. Okay, so let's figure out how to... So now, this gives us a map for how to break this up into these strips. But before we can actually numerically do this integral, we need a way to represent all of this stuff in terms of a single variable so we can integrate it. So let's make the variable that we're going to integrate with respect to x, okay? So then we're integrating with respect to this dx. We have this expressed in terms of x, you know, that x centroid. Is x. That y centroid is y over 2, right? That's just halfway up the height of that strip. So now, really the only thing we have left is to figure out how to represent the height of that strip in terms of x. So how do we do that? Well, the height of that strip follows the line equation for that diagonal. So y is equal to mx plus b. M is the rise over 1. So to get the slope of this, the rise of the whole thing is h, and the run is b. So y is equal to h over b times x. And the y-intercept, when x is equal to 0, y is equal to 0, because of where I put that origin. There's our formula for y. And so now that says that you know, we know that x bar is x, y bar is y over 2, which is h x over 2b. Stop me if there's anything you want me to slow down on, or and dA is the area of that strip, which is y dx, which is hx over b dx. Any questions about how I, yep. Because dA is the area of that strip. So what matters there is the height of the strip. So it's the whole height of this strip times the thickness dx gives us the area. Right. That's right.
What about the x?
This x bar equal to x? Because we're assuming this is infinitesimally thin, so this whole thing basically has the same x value as that dx shrinks down to 0.
Should we ignore the b? Because the b seems to be the non-bad. So.
Do we ignore the b?
Yeah.
For what?
The equation it was like the base was like b.
Mm-hmm. Yeah, so it comes up in calculating the slope of that line. That's where the b comes into it.
The other is 0. We had x to be like.
Oh, this? Oh, this b. Oh, yeah, I'm sorry. Yes, so when x is equal to 0, the height of that line is 0, so the y-intercept is 0. That's just using the slope-intercept form of a line. Okay, so now we have all these things defined. Let's just put them all together. So the centroid is equal to 1 over a. So I'll just take the reciprocal of this. So that's 2 over bh times the integral of x. So x bar, y bar. So x bar is x, y bar is hx over 2b. Times dA, which is hx over b dx. And what are the boundaries of integration? We're 0 to b, that's right. We're doing it in terms of x, so it's the x boundaries. And I'm going to pull all the constants out. So this h cancels with this h. And we get 2 over b squared times the integral from 0 to b of x squared hx squared over 2b squared dx. And now we can integrate that. So 2 over b squared times x to the third over 3 for the x component, and for the y component, h x to the third over 6b squared. That's evaluated from 0 to b. So that's 2b squared times b cubed over 3. And for the y, that's h b cubed over 6b squared. You can cancel a bunch of these b's. So those cancel with 2 of those, and they cancel with 2 of those. And so we end up with 2b over 3, the x component. And for the y component, we have 2/6, which is 1/3. H over b. What's going on here? So that should be, that's just a b. There should be just one b left here, right? H over b. And there's a 3 down here. So I think that went wrong. Let's find that. This one? Ooh, oh yeah. Because I pulled that b out. Thank you. Okay, so that's 2b. Now, and so we end up with h over 3. So I took this constant in the next step. I multiplied this by h over b, and then we just had the x to count. And so I should have, so I like double counted that b. All right, so what we're trying to find now is, so here's what we've found so far. If the centroid is here, we found that this distance is 2b over 3, and this distance is h over 3. What we really want, though, is this is what we want to call x bar. This is y bar, so we're good with that one because that was what I said we wanted. But if this whole length is b, okay, and the length from here to the centroid is 2/3 of b, what's the remaining length there? Yeah, that's b over 3, and so x bar is b over 3, y bar is h over 3. And so now, since we did this for a general H and B, there's no reason to use the integral formula anymore for right triangles, you know. So we can just use this formula for right triangles, future right triangles. And skip the integral, which is great. And so now what I'm going to give you, that's the way that all of these basic shapes that I'm going to give you centroid formulas for, it's how they were calculated originally. But once somebody's done the integral, nobody else had to. We just have these formulas that work. So here are some centroids for common shapes. The first is a right triangle. That's the one we just did. And so if this is B and this is H, we'll call this X bar and this Y bar. Then we need the area and we need the centroid location. The area is BH over 2. The X centroid is B over 3. And the Y centroid is H over 3. And the only thing you'll have to do with this is now you know that, like if you think of in the X direction and the Y direction, in both cases, what happens with the triangle is you have one side that's a point and one side that's a wall, And we've figured out that, like for example, if the base is B, you go a distance X bar, or B over 3, from the wall towards the point, okay? And the same idea works in the other direction. This triangle could be flipped though, or your origin could be over here, not over here, or not, And so you are going to have to think a little bit. All we know is the distance from the wall towards the point, but you're going to have to sort of flip that around in your head, translate that into new coordinate systems. The next thing is a half circle. The centroid is around there. The radius is R. And we want to figure out this Y bar. The X bar is going to be right on the midpoint. So we don't have to calculate that. The area is pi r squared over 2. And y bar is 4r over 3 pi. Then similarly, a quarter circle then the radius is one of those two sides. The centroid is here. So we'll call those x bar and y bar. The area is pi r squared over 4. And x bar and y bar are both equal to 4r over 3 pi. Fourth is a parabola. And we'll say that this dimension is h. That's the height. And then half of the width we'll call a. The centroid's up here. The x location of that centroid is along the midpoint, so we don't have to worry about that. We just have to calculate this y bar. The area of this shape is 4ah over 3. And y bar is equal to 3h over 5. And then the last one is a half parabola, semi-parabola. So the centroid is over here. This height is h. And this is a again. This is y bar, and x bar is from the midpoint of the parabola to the centroid. The area is half of the other one, so 3a over 8. No, 3. Yeah. 2a h over 3. Half of the area for the full one. And x bar is 3a over 8. And y bar is the same as it was for the full one, 3h over 5. Okay, so we're going to use those formulas for maybe every question. There might be one or something where you have to do the integration thing, but okay. But so what about shapes that aren't those 5 shapes that I gave you? It turns out that you can build up more complicated shapes as sums of these simple shapes. So building up complicated shapes from simple shapes. And like an example of that is, like what if you wanted to figure out the centroid of a person's body? I'm running out of room. Okay, so that's a person, break this all up into right triangles and rectangles and stuff like that. And so to calculate the center of mass of this person, we can break it up into all these things that we can use the formulas for, and then calculate the centroid of the whole thing using this sum formula. So that's a complicated shape made up of simple shapes. So the sum formula in 2D looks like this. X bar, Y bar for the whole shape is equal to 1 over the total area times the sum over all the individual simple shapes of the centroid of each simple shape times the area of the simple shape. And notice that sum formula is just exactly like the finite version of the integral definition of the centroid. Instead of an infinitesimal area dA, we have these individual small areas dA. We have the centroids of the individual pieces. So those two formulas should help you remember each other. It's the same exact idea. In 3D, it's the same stuff, but with volumes. So X bar, Y bar, Z bar is equal to 1 over the total volume times the sum from 1 to n of the centroid of the individual simple shape times the volume of the individual simple shape. Okay, so let's do an example. So let's say we have this T shape. Where the thickness of the top piece is 0.1 meters. The length of the top piece is 0.2 meters. The bottom piece is 0.05. And the height of the bottom piece is 0.2. I'm going to put the centroid, I'm going to put the origin right there. And we're going to calculate the location of the centroid by breaking this up into rectangle 1 up above and rectangle 2 below. All right, well, the centroids of individual rectangles, sorry, I'm going to move these so we can, okay, so what did I call them? The top one was 1. So the centroid of the top one, with rectangles, it's just the centroid is right in the middle in both directions. 2 is the bottom one, and the centroid of that is right in the middle of that rectangle. So let's figure out what we need for each of these 2 rectangles to calculate the centroid of the overall thing. Rectangle 1, we need the area, and that's 0.1 times 0.2, so 0.02 meters squared. And we need the centroid. So now, to find the centroid, the middle of this rectangle is right above the origin. So there's not going to be any x component to that centroid, but the y component of the centroid is going to be up 0.2 to get here, and then up another 0.05 to get from here to here. So 0.25. So 0.25. And then for the bottom one, the area is 0.05 times 0.2. So that's 0.01 meters squared. And the centroid of the second rectangle is 0 for x. And then for y, you have to go from the origin up 0.1. So 1.1. All right, and then we need the total area. That's just going to be the sum of the two individual areas, so that's 0.03. Now using that, the overall centroid is equal to 1 over 0.03 times the centroid of the first piece times its area plus the centroid of the second piece times its area and that gives you a total centroid (0 for x, 0.2 for y). So the overall centroid for this shape is right at the line between those two. Any questions about that? By the way, you can also use this sum formula to remove material. So let's think about a square where, well, let's make it a rectangle, and we'll remove a semicircle like that. And find the centroid of Minnesota. So no, that could have been a square. Let's make it a square. Okay, so we'll make this length 1. This length is 1. And that means that this circle has a radius of 0.5. And I'll use a coordinate system with an origin down at the bottom corner. Okay, so we have a big overall shape, and then we're removing a semicircle from it. The big overall shape has an area, so I'll call this one shape 1, and this is shape 2. So A1 is 1 times 1, so 1. And the centroid, what's the centroid of that square? It's just right in the middle. So you go in the positive x direction, 0.5, positive y direction, 0.5. So x1 bar, y1 bar. is 0.5, 0.5. Now the area of that inner circle is pi r squared over 2. Pi r squared is 0.25 pi, and then over 2, so I guess that's pi over 8. And the centroid of that shape, so now we have to think a little bit. The formula that we were given for a semicircle gave us the distance from like the midpoint, the slice of the circle, out towards the top of the circle. And that distance, so that's the distance like from here to the centroid, was 4r over 3 pi. And then we also know that it's right on the center line this way. So our y bar is just going to be half the way up. And the y bar is just going to be 0.5. And the x bar is going to be, you can think of that as, if we know that it's 1 to get from here to here. And then we know it's 4r over 3 pi to get from here back there. So it's going to be 1 minus 4r over 3 pi. Uh, 4r over 3 pi. And that r is 0.5, so that's just, I don't know if there's a clean way to write this, but 1 over 2 over 3 pi, and then 0.5 for y. Now, what's the total area of this, of the complicated shape? I don't know, I just don't have a calculator here, so I figured we'd, but no, I don't care. You can just write that as a decimal right from the start. So the total area is, the big shape minus the removed shape. So that's 8 minus pi over 8. And can you tell me what some of these values are? So in decimals, what's pi over 8?
Pi over 8 is
3926. And what's 1 minus 2 over 3 pi?
Gives me a negative 1.0944.
Something, your pi ended up on top somehow or something. Seven, 8, 7, 8. Okay, and this one is, well, 1 minus this, so 0.5074. 6074. Okay, so now we'll put it into the formula. So the centroid is equal to 1 over the total area times the centroid of the rectangle times its area minus the centroid of the removed shape times its area the y component, since both of those have the same centroid of 0.5, that y centroid is going to be 0.5. Can someone calculate what the x component is going to be? So somewhere over here, like Detroit Lakes. Any questions about that? Okay, one thing to notice is the centroid always lies on any line of symmetry in 2D. So in 2D, the centroid lies on any line of symmetry. So if you can find two different lines of symmetry, the centroid is where they intersect. It's at the intersection of any two lines of symmetry. So for example, a shape like this. There's one line of symmetry like that, so you know the centroid has to lie on that dotted line. And so in this case, you could use that fact and know that all you have to do is calculate the vertical location of the centroid. And then this is always is also why I didn't give you formulas for the centroid locations for rectangles or circles. A rectangle has a line of symmetry like that and one like that, so the centroid has to be here. And same thing for a circle. It has infinitely many lines of symmetry, and they all meet at the centroid. The centroid doesn't take that into account. It's only the center of mass that takes that into account. But I think we do use the centroid pretty often to find the center of mass, and I think in every case in this class, yeah, we'll assume that it's homogeneous. Any other questions? Okay, so that's why, like if you look at these formulas, like for the half circle and the parabola, I didn't even give a calculation for the horizontal location of the centroid because both of those are symmetric about vertical lines. So the centroid has to lie on this vertical line and it has to lie on that vertical line. Also, for the quarter circle, you can see there's a line of symmetry like this. It just doesn't end up being super, like, it's more complicated to figure out where that line is than it would be to just use that formula twice, so we didn't take advantage of that. All right, let's do, what do we have? Let's do an example where we use a centroid to calculate the center of mass. Oh, whoops. I went all NC Escher on that. Okay, so let's say we got a thing like that. The thickness is, let's say it's 0.1 meters. And let's say that the height this way is 1.1 meters. And this way is 1 meter. And let's say that there's also a, let's say there's a roller there. And the mass of this object is 20 kilograms. What are the reactions at the joints? Okay, well, the only thing that's causing reactions at all is the weight. But we're going to have to calculate the centroid to figure out where the weight is applied. So I'm going to break it up into a rectangle like this and a rectangle like this. Here's rectangle 1 and rectangle 2. I'll put the coordinate system over here. The centroid of piece 1 is there, and piece 2 is here. So the area of piece 1, you know, the way I divided it up, they both have thicknesses of 0.1 and lengths of 1. A1 is equal to 0.1. 0.1 times 1. And the centroid of piece 1 okay, so you have to go in the negative x direction. How far do you have to go to get to the middle of this thing? I guess the middle this way is 0.05 meters from either side, right? So you have to go 0.9 meters to get here, and then another 0.05 meters to get there. So negative 0.95. And then to get to the centroid this way, you have to go 0.05 meters up, since this is in the middle. Okay? You have to go 0.05 meters up to get to the bottom of this. And then you have to go up 0.5 to get to the middle. So this is 0.55 meters up. And then for the second piece, the area is 0.1 again. The centroid in the x direction, you have to go negative 0.5. In the y direction, we don't have to go anywhere. So this is negative 0.50. The total area is the sum of those two areas, so 0.2. And so the overall centroid is equal to 1 over 0.2 times negative 0.95, positive 0.55, times 0.1, plus negative 0.50 times 0.1. And that is, can someone calculate that? Negative point, seems like it should be farther back. What was the y one? 0.275. It needs to be farther, it needs to be a bigger negative number for the x one for sure, because, okay. Negative 0.725. Okay. Okay. All right, so that's where, now that is the location where the weight is going to be applied. So now we can finally draw a free body diagram. So we have a weight force acting like here. Notice that that's not even, the center of mass doesn't have to be on the material at all. That makes sense if you think about like a ring or something. You know, like a ring, clearly the centroid has to be right where all those lines of symmetry meet, but there's no material at that location. This thing has a mass of, what did I say, 20? So the weight is 196.2. Then there's an unknown force vector here at the pin joint. We'll call that RA. And then from the roller, there's a force perpendicular to the surface toward the chosen body. So I'll label that with the scalar RB. And then rho, force, moment. Okay, so that force RA is applied at the origin, and that's where we're going to choose our about point. So the rho vector is 0, 0. The force vector is RAX, RAY. and there's no moment. Then the weight force, since our origin is our about point, we can just use that centroid location as the row vector. That's sort of a nice thing about having your about point and your origin in the same spot. So that's negative 0.725, positive 0.275, and the force is 0, negative 196.2. Can someone multiply 0.725 times 196.2? $142.2. And then the last one is this horizontal force RB. The only thing that's sort of a hassle about that is figuring out the X location, but we don't even have to do that because its line of action is horizontal. So all we have to figure out is the Y location. RB the row vector is 1.05 in the, so we'll call it 0 in X, 1.05 in Y. The force vector is positive RB 0. And so the moment is negative 1.05 RB. You know, Arby's Restaurants pays me $500,000 a year to use that variable over and over again. That's why I drive a Ferrari, if you've ever seen me. Yeah, exactly. Usually I ride my bike. Okay, they don't give me any money. They should. Okay, so Newton's second law says RAX, RAY plus 0, negative 196.2 plus RB0 equal to zeros. And the moment equation says 142.2 minus 1.05 RB is equal to 0. So what's 142.2 divided by 1.05? Okay, so the force RB is 135.5 newtons. And RA, the Y component is 196.2. And the X component is negative 135.5. And you can't do that problem without finding the centroid, because you'd put the weight force in the wrong place and you'd get the wrong moments, wrong answers. Any questions? That was the centroid. That was the centroid of that shape. Okay, see you Tuesday. I'll try to get your binders back.